In this video, we're going to talk about inverse functions. So we've learned about functions and ways to combine functions and the definition of a function. I'm going to draw a quick picture about functions, okay? So when we've got a domain and we send something in our domain to our range, okay? Domain and range, okay? Well, this function that sends this x value over to, I'm going to just call this y, all right? We'd like to know if there's a way that we can go backwards, all right? Is there something that takes this y and sends it back to x, okay? And if so, we're going to give it a special name, all right? Because it's connected to this function f, we're going to call it f with this superscript of -1, okay? This is read f inverse, okay? So let's talk about finding these inverse functions. There's a set process that we follow, and it's very straightforward. Okay, to find the inverse of a function, we set y equal to our function. We have y equals our expression with x's in it. Okay, then we switch x and y because we know that that's what an inverse does. It changes our domain and our range. It flips around the direction that we're going. Okay, and then we solve for y, and what you end up with is the inverse function. So here's an example. This is a simple one. Let f of x equal f of x, or sorry, 4x plus 1. And so we want to find the inverse of that. We start by setting y equal to that thing. Okay, then we're going to switch x and y. So just everywhere we see y, write it as x, and everywhere we see x, write it as y. And then we want to solve for y. So this one's straightforward. We subtract 1 from both sides. And then we can divide both sides by 4. We have x minus 1 over 4 equals y. Once you have y by itself, then you've got your inverse function. So f inverse of x equals x minus 1 over 4. Notice that the inverse here is simply doing the exact opposite of what the function does. This function takes an input, multiplies it by 4, and then adds 1. So to undo that, to go backwards, we do the opposite. We subtract 1, and then we divide by 4. And that's our inverse function. Let's do another one. Find the inverse of f of x equals 3 minus 4x cubed. So we start off with y equals our function. Then we switch x and y. X equals 3 minus 4y cubed. Okay, now we want to get y by itself. Subtract 3 from both sides, and we get x minus 3 equals negative 4y cubed. Then we need to divide by this negative 4. So x minus 3 over negative 4 equals y cubed. And now to get y by itself, we need to get rid of this cubed. So we need to do the cube root. So that's x minus 3 over negative 4, and then the cube root of that equals y. Once you've got y by itself, you've got your inverse function. F inverse of x equals the cube root of x minus 3 over negative 4. Here's a harder one. We've got find the inverse of f of x equals 5 minus x over 3x plus 2. Okay, so these types of this is where it really gets interesting for us, all right? Getting the inverse of this function. We start off with our y equals the function 5 minus x over 3x plus 2. Okay, we switch x and y, so we now have x equals 5 minus y over 3y plus 2. So we want to solve for y, and y is showing up twice here, so it gets a little bit trickier, but it's a pretty straightforward thing if you just remember our steps. We don't like the fraction. So what we're going to do is multiply both sides by that denominator, 3y plus 2. Okay? So it gets rid of the denominator on the right side, and on the left side, I'm going to go and distribute the x. So we get 3xy plus 2x equals 5 minus y. So now, since I'm trying to solve for y, I'm going to get all the y's together and move everything else away from it. Okay? So I'm going to subtract 2x from both sides. 3xy equals 5 minus y minus 2x. And then I'm going to add this y to the left side. So I've got 3xy plus y equals 5 minus 2x. Now the reason that's helpful is because I can now factor the y out. And we're left with 3x plus 1 there. Minus 2x. All right, well, now to get y by itself, we just need to divide by the 3x plus 1. So y equals 5 minus 2x over 3x plus 1. And there is our inverse function, since we've got y by itself. F inverse of x equals 5 minus 2x over 3x plus 1. Now, given two functions, we'd like to be able to verify that the functions are inverses of each other, okay? And to do that, we just need to know the property that inverse functions cancel each other out. In other words, we want f of f inverse of x to equal x, and we want f inverse of f of x to equal x. Both of these should be true for inverse functions. Okay, here I've got this. I got a little typo here. This is an f of x right there. All right. I want to verify that this 2x plus 1 is the inverse of x minus 1 over 2. So all we're going to do here is plug them in. So f of f inverse of x. I'll go ahead and plug it in. F inverse of x I have it as 2x plus 1. Okay. We take that and plug it into this function. So I'm just going to take the 2x plus 1 and put it into that x. So 2x plus 1. And then we have this minus 1. And then we have the divided by 2. Well, now we just simplify. The ones cancel each other out, so we have 2x over 2. And of course, 2x over 2 is just x. So that one worked out. We also want to do f inverse of f of x, which is x minus 1 over 2. So f inverse takes 2 times our input, x minus 1 over 2, and then adds 1. Well, now the 2's cancel here, and we have x minus 1 plus 1. Well, the negative 1 and the plus 1 cancel each other out, and again, we just have x. So we have verified by doing both of these things and getting x for both of them. We have verified that these are inverses of each other. Another important feature of inverse graphs is, of inverse functions is how the graph of an inverse relates to the graph of a function. So we have this property here. The graph of f inverse is the reflection of the graph of f in the line y equals x. So I'm just going to draw a quick picture here. So it doesn't really matter what this function is. You should be able to recognize this as a square root function that's been transformed. But we're going to draw the line y equals x. Okay, so you can see how this works. We take the line y equals x, and the inverse, okay, if I wanted to graph the inverse of this function, call this f, we want to flip it across this line here. And so what that means is each point that we have, we can just switch the x and the y coordinates. So this point here is at negative 4, 0. So we could flip that and do 0, negative 4. That would be a point on our inverse graph. Okay, we've also got this point here that's at negative 3, 1. We could flip that and do 1, negative 3. Okay, and you can do that with as many points as you want. The point that intersects the line y equals x will be on both. All right, and you don't have to be super precise about this, but just try and get it to look like the reflection. All right, so this right here would then be the graph of f inverse. So we'll talk about verifying inverse functions graphically. So verify graphically that the functions f of x equals x squared with x greater than or equal to 0 and g of x equal to the square root of x are inverse functions of each other. So, well, that's we can go ahead and graph these, and we could do it with a graphing calculator or with just by hand. I'm going to go ahead and just do it in the graphing calculator since we're learning it right now. So we'll go ahead and graph the x squared. And in the calculator, to restrict the domain, what we're going to do is we're going to do control and then the equal sign. Okay, and then we're going to do this vertical bar. That vertical bar means such that it means restrict to a certain condition, all right? So we'll do that, and then we'll type in our restriction, which is x, and then the control equals, again, to get greater than or equal to 0. All right, and we hit enter, and see it gives us that portion of the graph. And then we want to graph this other function, so I'll do tab to get a new function, and then we do our square root of x, and hit enter, and look, there we've got our graphs. And notice, okay, if it's hard to see, you can graph the line y equals x as well. Graph y equals x, okay, and we see that line, and we can go ahead and zoom in if we'd like. I'm going to go ahead and do that, and I'm going to do a zoom box and just kind of look at what we've got there. Okay, and so we see that our graphs are reflections of each other in the line y equals x. And so we've verified graphically that these functions are inverses of each other. Notice that we have this restriction placed on x squared for x greater than or equal to 0. The reason that is that if we had it on the other side as well, well then our square root of graph wouldn't be enough. We'd have to like come back down and come around. But of course that would not pass the vertical line test, and so the function, the inverse would not even be a function. So let's now talk about some more details about knowing if a function has an inverse, because not every function has an inverse. Okay, as we just saw, x squared if we try and reflect that, we get something that doesn't pass the vertical line test. So we need to talk about a definition here first. A function is said to be one-to-one when each value of the dependent variable, that's the y, okay, corresponds to exactly one value of the independent variable, x. This means we can't get the same output with different inputs. All right, so it's kind of the backwards of the definition of a function. Okay, we can't have, so for example, x squared fails this because 4 is an output for x squared that comes from two different inputs. It comes from -2 and from +2. So x squared is not a one-to-one function. Okay, and then it turns out that the one-to-one functions are the ones that have inverse functions. All right, now with that, we can check this graphically using the horizontal line test. Okay, the horizontal line test says that a function f is one-to-one if and only if no horizontal line intersects the graph of f at more than one point. So here what I've drawn is an example of a function that is not one-to-one, because there's a horizontal line that crosses our graph more than once. Okay, so if a horizontal line crosses more than once, your function is not one-to-one, and so it won't have an inverse. Another way that you can check is just in a table. All right, if you have a table of values for a function, to check to see if it's a one-to-one function, you need to check to see if you have any output that shows up more than once. Okay, if you do, the inputs cannot be different for a one-to-one function. All right. Well, here notice that we've got the output of 4 in two different places, and the inputs are different. Same thing for the output of 1. The inputs are different. This is not a one-to-one function. Not a one-to-one. Oh, that's not a one-to-one function, because we have because two inputs give the same output. Okay, so that negates this from being a one-to-one function.